first thing we need to know is that even though there are three, remember there are three invariants, I1, I2, and I3. The first one is called the trace of T. The second one is the trace of the cofactor of T. And the third one is the determinant of T. So there are three principal invariants: the trace of T, the trace of the cofactor of T, and the determinant of T. These three principal invariants are completely independent of the choice of A, B, C. You can choose any three linearly independent vectors, you are going to get the same result. So the invariants, the scalar functions are invariant, and they are the principal invariants of any tensor. Most of the time, whenever you are dealing with a tensor quantity, those are the things that you are really looking for. The tensor itself is not as important as its scalar invariants. Those scalar invariants, called principal invariants, tell you most of the physical attributes, whether the tensor is a stress, whether it is a strain, whatever it is, the scalar invariants are often more important than the tensors themselves. The first thing you notice is that out of the three, the first one is linear on its own, is a linear function of the tensor, but the other ones are not linear. The trace is a linear function. The trace of the cofactor is not linear, and the determinant of a tensor is a nonlinear function of a tensor. So what we mean is that if you have two tensors, A and B, the determinant of A plus B is not the determinant of A plus the determinant of B. The trace of the cofactor of A and B plus B is not the same thing as the trace of the cofactor of A plus the trace of the cofactor of B. But the trace of A plus the trace of B will give you the trace of A plus B. So the trace is a linear function on the tensors, but the others are not linear. So here, I1 of alpha T plus BS, where alpha is a scalar and beta is a scalar, and T and S are tensors, will give you this. Now, if you look at this, on the first line here, all we have done is that we apply, instead of T alone now, we use T, alpha T plus BS in each of the brackets. That's all we did. So the first line is just a definition. The second line, we expanded each of the brackets. Now, if moving from here to here gives you a problem, if it gives you a challenge, if it's not obvious to you that we can move from this first line to the second line, what I will advise you to do is to look at page 36 in this slide. I have expanded that second step. I'm not going to talk about it. I've expanded it. So if you read what is in the note and you read the next page with it, you should be able to understand it. So if you have any difficulty further on, let me know. So we have established the three principal invariants, and we have shown that the first invariant is linear, whereas the remaining two invariants are not linear. The remaining two invariants are not linear. In chapter 1, we use this simple trick to find a dyad, the trace of a dyad. You know, a dyad has a circle times. If you change that circle times to dot, you are getting the trace. To get the trace of a dyad is very easy. Take the tensor product inside it and change it to dot. Then what you have left is the trace of the dyad. We can show that this computation is correct. We can prove it, and we are going to do that in the next page. Let us say you want the trace of U circle times V, which is I1 U circle times V. That means that instead of T here now, you put U circle times, all the places you have put T, U circle times V. And then you expand it. If you expand it, you know that if you want to expand this first expression here, you have to take the dot product of V and E1, which gives you the first component of V. And you still have the vector U and then E2, E3. You do that in each of the brackets, you have this. The next thing is this line. On this line, what the issue here is E2 cross E3. What is E2 cross E3? To get E2 cross E3, remember that A dot B is EIJK, which is our usual alternative symbol, AIBJ, BK, EI being the base vector. So if you do that with E2 and E3, knowing that E2 is 0, 1, 0, and E3 is 0, 0, 1. In E2, you eat in the afternoon. In E3, you eat only in the evening. So 0, 1, 0, and 0, 0, 1. So you have those two. Now, if you substitute that into this, you will just simply get E2, 3I, EI. That's what you get. If you only one, only that expression, that is the only thing that survives. All the other things vanish. Similarly, you have this one here is E31I, EI, and this one is E12I, EI, and so on. So if you open up everything, you just get U dot V. So we are proved on this page that the trace of U circle times V is simply U dot V. Again, please go through this meticulously, and if you have any problem with a step there, do not gloss over it until you understand it. And if none of your classmates can help you in that, I will help you. This is where I can help you. Don't wait until the end of the term and be asking me for marks. Let us discuss now. If you discuss with me during the term, I will likely listen to you at the end of the term. But if you don't do anything, you are sleeping throughout, and then you just suddenly wake up at the end of the term, you want more marks. You're wasting your time. That's not what my phone number or my email address is for. You don't start using my email. You are abusing it if you are thinking you use it to be disturbing me. Okay, so the trace of a tensor in component form, beginning from the component representation T is equal to Tij EI circle times EJ, which we discovered last week. We can take the trace of both sides. Take the trace of T and take the trace of this, noting that the trace of a dyad is simply changing the dyad to changing the tensor product to a dot. And if this one becomes EI dot EJ, it just becomes delta IJ, and Tij delta IJ is Tii, which is T11 plus T22 plus T33. Don't forget that since I is repeated here, that denotes summation. So the trace of, and in many textbooks, this is used as the definition of trace, just some T11 plus T22 plus T33, but it's not the fundamental. We can get this definition, we can get this result from the original definition. So that's it. So as we have shown earlier that the trace of a dyad is the scalar product of its operands, we note that transposing a tensor does not alter its trace. If you take the trace of a tensor or take the trace of its transpose, you are getting the same answer. Transposing a tensor does not change its trace. Now, the second thing is the trace of the cofactor. Here, we are trying to find the trace of the cofactor in component form. How do we do that? We do that, the first line here, what we did is to change this T to its, we changed the T to what we did before. We changed it to this Tij EI circle times EJ. So instead of T here, we have Tij E circle times EJ. Here, instead of T, we say T alpha beta E alpha E beta. So we don't want to use Ig so as not to confuse them. Similarly, alpha beta here, Ij here. So you just change all the occurrences of T to the component form. And then the other vectors that are there too, you change them to their component form. And here, instead of A, B, and C, you use E1, E2, and E3. Because you remember, it does not matter what the three independent vectors you use. You can use any three independent vectors, linearly dependent vectors. So why don't you just use the simplest one, E1, E2, and E3, whose triple product is 1. So there's nothing below any longer, since what is below is 1. So if you do that, and by the time you expand that, you just see that tensor components are scalars, so you can take alpha and beta out. You can take alpha and beta out. So if you have alpha A dot beta B cross C, you can take alpha beta A dot B cross C. So you can do that. After doing all of that, we arrive at this. Again, I'm not going to go further than that, but on your own, go deeper into that and make sure that you can move from one line to the other. Because if you can't, when you get some of these things in a test, you will just find out. I can ask you in a test to show that this one is equal to this. I can give you this formula, and I will write several things that will be using you. So you need to choose one of them. And if you did not do it yourself, it will not be possible for you to be able to see which one is the correct one. So check through this. So if you continue, you see that the trace of the cofactor is half of Tii Tjj minus Tij Tji, which is half of the square of the trace minus the trace of the square of the original tensor. In several books, this is used as the definition of the second principal invariant. In several other books, you look for the trace. This formula is used to define the trace. But you should see here, we used a more fundamental definition and then obtain this one. The last one is the determinant. The determinant of a tensor. If you use E1, E2, E3, since we can use any three independent, linearly dependent vectors as the basis, so if we do that, this is what we get. You see that if you take again the tensor in the component form, Tij here, T alpha beta here, TRS here, and you open these ones. If you open these ones, what do you open? You see that there is a circle times here. So this one will be Ej E1. So that's delta J1. Delta J1 will only be equal to E1. Delta J1 will be equal to, so that J1 will be equal to E1. So that is what, so if you do that, then that gives you Tij with this, you get Ti1 EI here. So if you keep opening one day one by one, you are going to get these results one by one there. And at the end of the day, you have Ti1, Tj2, Tk3, Eijk. And that is also the definition of the determinant of T. In component form, this is what it is. How many terms are here? Can somebody tell me how many terms are inside that? Okay, so you can see there are 27 of them because we are summing over I, over J, and over K. Good. So that is, okay, so we have here a poser on linearity. While the trace is a linear scalar function of its tensor argument, the trace of the cofactor and determinant are not. The inverse and the cofactor are tensor functions of the same tensor argument. They are non-linear functions. Does this contradict the earlier assertion that the inverse transformation is a linear transformation and therefore a tensor? I want you to come to the next lecture with your answer to that. Does this contradict the earlier assertion? The inverse and the cofactor are non-linear functions of the tensor argument. But we said before that the inverse of a tensor is a tensor, which means it performs linear operations. But here we are saying it is not a linear function of a tensor argument. I want you to disambiguate these two seemingly contradictory statements. So is the tensor inverse, is it linear or non-linear? Here we say it's not linear in its function, in its argument. Previously we say it is linear in its operation. So explain, try and understand those two, because if not, you can easily get confused. Now, we want to show here that the determinant of a product of two tensors is the product of the determinants. If you have two tensors and multiplying each other in a composition, A and B are two tensors, AB is the composition product of the two tensors. What is the determinant of that composition? We say that the determinant of the composition is the determinants of A multiplied by the determinant of B. How do you prove that to be true? Select linearly dependent vectors A, B, and C. And if B is not singular, it is easy to show, if B is not singular, that we can get new vectors U equal to BA, V is equal to BB, and W is equal to BC, which will also be linearly independent. Therefore, if you try to take the determinant of AB, it is ABA, ABB, ABC over ABC. You can get this. You can say it's equal to this. In this second equality, what you should notice is that BABC is dividing on this side, is multiplying on this side. You can cross the two out. But we're not going to cross the two out because it is interesting for us to look at this, what we have here. So if we can say U is BA, V is BP, and W is BC, you can see that we can write U for BA, V for BP, and W for BC. U for BA, V for BP, and W for BC. In that case, this is also the determinant of A because it is three dependent vectors, AU, AV, AW over UVW. And similarly, this is the determinant of B because ABC gives you the vector basis to get the determinant with. So that becomes the determinant of A times the determinant of B. So the determinant of a composition is the product of the determinants, proved, complete on this page. Now, the next thing we want to look at is the inner product of two tensors. You already know what the dot product of two vectors are. In this expression, in this page, we are going to define something new. That is the inner product of two tensors. If you have two tensors S and T, when we are dealing with inner product of vectors, we use a single dot. When we are dealing with inner product of tensors, we use a double dot. The double dot is signifying that we are looking at a second order quantity, whereas in the single dot, we are looking at the first order quantity. So that is just the symbolism. By definition, it is if you want to get the trace of a composition, you take the transpose of one of them before doing the composition, and then it doesn't matter whether it is the first one you transpose or the second one. So it is the trace of S transpose T or the trace of S T transpose. You are going to get the same answer, and that answer is called the inner product of the two tensors. Let me repeat myself. You have two tensors S and T, and you want to take the inner product of their composition. You just don't go straight to the composition. You take the transpose of one and do a composition with the other one. Either the transpose of one with the other one, or the one with the transpose of the other. If you do that, you get what is called the inner product of the two tensors. For a tensor, so what we are going to do next is we are now going to find that inner product in component 4. Remember that T is equal to T alpha beta E alpha circle times E beta. This definition leads to a simple formula for the components of tensors, as we shall show. Consider the composition T being composed with EJ, EI. We take the trace of the composition to obtain trace of EJ, EI, which is the same thing as trace of T alpha beta, E alpha, E beta, EJ, EI. So you remember that when we are composing two dyads, we just take the first thing and the last thing and take the dot product of the two that are near. So that gives you what you have on the third line here. When that gives you what you have on the third line here, so you see that it is simply T alpha beta, E alpha, EI here, plus delta J beta. So instead of beta, we can just put J. So if you bring those things out, you see that everything is simply this quantity here. So it becomes T alpha beta, delta I alpha I beta, delta beta J, which gives you Tij. So that is Tij here. So from the above definition, the scalar components of the tensor on dyad basis, so you have now that Tij is equal to the trace of T into this, which is the same thing as T colon EI circle times EJ. So the component of the vector we had before is also the same thing as the inner product of that vector, of that tensor. The component of the vector tensor is the inner product of that tensor with the tensor base, which is the same thing that you did if you knew in vectors. You want to get the component of a vector, take the inner product with the base. Similarly, that same rule applies to tensors. The definition of inner product leads to a simple way to compute the component of vectors, the tensors. Just like vectors, is simply taking the inner product with the product base, and it will give you the answer you are looking for. Okay, I think that's the last slide. Let's see what time we have. You still have a lot of time, 12:25. Well, let's see. I'm going to allow you to ask me questions for the next 2 minutes. If there are questions, I wait with you. Questions on today's topic? There are questions. If there is any slide you want me to help you more with, let me know. If there are any questions, how did okay, so that's which slide? Is it the page 43? 45? What page? James Wood.tongue. What page? James, what page? What slide? What slide number? 45? Is it on? James, 45. Okay, good. Which line are you talking about? Is it the second to the last line? Let's see. How did E alpha diad E beta become chronicle delta? E alpha diad E beta. No, what are you talking about? What are you talking about, James? James, you are forgetting something. You are forgetting something, James. Let me show you what you are forgetting that we have dealt with. James, do you remember this page 22? What happens when you are doing the composition of a chain of dyads? James, do you remember slide 22, James? James, can you answer me? Can you see, I'm displaying slide 22 for your benefit. Is James still there? James Wood.tongue. Okay, he says he's talking about the last line. James, don't forget that we are taking the trace. We are taking the trace. If we are taking trace, we are going to change the circle times to dot. And when we change the circle times to dot, it becomes delta alpha I. Because these are base vectors. If we change this to a dot, remember there's a trace here. The trace means that everything else inside this bracket is scalar. So the trace applies only to this product. So we are changing this to a dot. If we are taking the trace of this bracket, this must become a dot. And E alpha dot EI is delta I, is delta alpha I. I wonder why James is suddenly quiet, not talking again. Oh, yes, you didn't hear my explanation then. What I'm saying is that for your question, if we are taking the trace, we have to take this, we have to turn this to a dot. If we are taking the trace, we have to turn this to a dot. And once we turn it to a dot, it becomes delta alpha I. Okay. Okay, it's clear. Yes, James has finally woken up from the dead. He says it's clear now. Good. James is back. It's clear to him now. Okay, there's no other question.